if you look in the 7.4 section, you will find videos already of how to work problems. But since y'all are a day behind on getting notes about it, not by your fault, but just because I got lazy yesterday, I'm going to pick out some of the questions they've been asking me today and chat with you about them. Okay? We'll start off with number 6. Number 6. And this is 7.4 in the Sisson. I'm going to start with number 6, and I'm just going to kind of work down and show you some of the questions. Now, when I write this, I like to put the 2x in parentheses just because it's a habit, but you don't have to. And like so. Now, what happens here is if you try to bring the cosine x and subtract this from both sides, it's going to be hard to factor it out. But what I'm hoping is everybody realizes if you divide this side by cosine 2x, all right, or multiply by 1 over cosine 2x, multiply by that. That's going to make a tangent 2x right there. Is that all right? Because you're going to multiply by 1 over cosine 2x, that's going to be sine over cosine, that's going to be a tangent 2x. Now, tangent 2x. Then, that's just going to be square root of 3 because cosine 2x over cosine 2x is 1. And the reason I like that is now I only have one trig function. If I can ever write it to where I only have one trig function, life is pretty easy. It's when you have multiple trig functions, it makes it a little bit harder. But if you can ever rewrite them, that helps. Okay? Now, once I get there and I see I have that 2x, that's when I got to do my little trick about substituting in theta. The people that are coming back and asking me questions are not willing to write this down. Theta is going to equal the 2x. So then tangent of theta is equal to square root of 3. And then you make a list of what the theta is equal. And you write theta so you'll know what they are. Okay, the tangent of theta equals the square root of 3, and I'm going around the unit circle. Now, if you do not have a good unit circle, I got some more purple pages run off. Monday of next week, if you don't have a good unit circle, you can just forget it. You're going to fail. Oh, let's say this. If you have a good unit circle, you have a really good chance of being all right. Okay? So you look around that unit circle and tell me what theta values are we talking about? We're talking about what? Pi over, how much? Pi over 3. And where else if you go all the way around the circle? 4 over 3. Now, that went around the circle one time. But I got to go around the circle how many times? 2. So I'm going to add 2 pi to every one of those. And 2 pi is the same thing as 6/3 pi. Does everybody agree 2 pi is the same thing as 6/3 from our math in the 6th grade of adding? So, 6/3, that's going to make a 7/3 pi. And that's going to make a 10/3 pi. You have now gone around the circle twice. And what tells you have to go around the circle twice? The fact that you wrote that down like I told you to. Those are your thetas. If you write those on your test, too bad, you missed it. Because you got to do what? Turn them back into x. Now, to do that, x equals 1/2 theta. Somebody says, how'd you know that? Because if theta equals 2x, then x is equal to what? 1/2 theta. Do you see how important it is to write this down? It's telling you how many times to go around the circle. It's telling you the information right here. It's important. Folks, you can't do math with any less work than I put into it. All right? Because I'm that lazy. So, you're going to write your x answers. Half of that, pi over 6. Half of that is 4/6 which reduces to what? 2/3. Half of that, 7/6. Half of that is 10/6, which reduces to 5/3. And those are all four of your correct answers. Mr. Evans, I'm just going to put the first two on the test, see how I do. Okay, you get a 50%. Yeah. All right. But that's one where I just want to show you, I wanted to concentrate on this part, and I also want to show you how you can get to make that tangent, make it a little prettier. Now I'm going to let you look at it a second, because I got to realize I've taught this 4 times. Fourth time I've taught it, so it's not the 4th time you've seen it. So give you a second to look at it. Anyone? Questions? All right, I'm not going to pull the college stunt and only teach the top few people in class. All right. We'll come back to that. I'm going to go down because I kind of had another one down here. Number 30 is an easy problem. It just takes a little bit of thought. Number 30. Number 30. And you may already know why I'm picking that problem out. It's got sine negative x. We haven't seen that. Equals 5 sine x plus 3. All right. On the back of your circle, there should be a few little rules. And if I didn't give them to you, here they are, and you can see if they're already back there. Here's a couple of things that'll help you. These are big rules for the back of your circle. Add these to the back of your circle. The cosine of a negative theta equals the same thing as the cosine of a positive theta. So if you ever see cosine negative theta, what do you do on the very next step? You just write cosine of positive theta. Fair enough? Now, the sine of negative theta equals the negative of a sine of a positive theta. Now, on this one, somebody says, do you factor that negative sign out? No, no, no. Because if you were factoring the negative sign out, this one would be negative 2, wouldn't it? It is just a trig identity. That's how it works. And I can show you why. I may even show you why. Same thing for tangent. If you have the tangent of a negative theta, don't try to work that. Just make it negative tangent theta. But cosine negative theta equals the same thing as just cosine positive theta. There is no negative sign out front. All right? Put those on the back of your circle because they'll come in handy. And that's all you got to know in order to deal with this problem, is to get around that sine of a negative x. Put those 3 identities on the back of your circle. Okay. If you do that, you make that negative sine x equals 5 sine x plus 3. Subtract 5x, you get negative 6 sine x equals 3. Sine x equals negative 1/2, and then just start doing what? Look on your circle. Is everybody okay with that? Look on your circle. I kind of went through that fast. I know y'all can do all that algebra. But right there is a key step. Please make sure you got these 3 rules written down, because you don't want to put a negative sign out front if it's cosine. If it's cosine negative theta, it equals just what? Cosine theta. And then sine x equals negative 1/2. X equals pi over what? How about 7/6 pi? And what? 11/6 pi. Am I right about that? How many of you have your circle? How many of you can read your circle? If you do not have a good circle, tell me. Do you have a good circle?
Mm-hmm.
Where is it?
I forgot my notebook at home.
Okay, but you do have a good circle. Okay. My little Johnny didn't have a circle. He didn't know you needed it. Little Johnny ain't gonna make it in college. Girls don't need to date little Johnny because he ain't never gonna be able to do anything on his own. Mama's gonna have to hold his hand. Okay.
Mr. Rivers,
Yes, ma'am.
where it says 5 sin x minus 3, did you do something to make it plus 3?
Oh, I just wrote it down wrong. My fault. Yeah, I wrote the problem down wrong. Matter of fact, I'll fix it. Yeah, I just wrote the problem down wrong. That should be a minus, so that should be a positive right there. And then I should have gotten what? Pi over 6 and 5, 6 pi. Kept wondering why you kept looking at that problem. Yeah, all right. Yeah, I just wrote it down wrong. Now, 29. 29. And somebody says, wait, you don't work 29 because 28 and 29 you can't do without a calculator. If you look at your list of problems that I assigned, I avoided anything you'd have to have a calculator for. Yeah, all right. I got the next problem we'll look at. Oh, right here. Number 63. 63. Yeah, we took a big jump down the page. Now, like I say, these are the same kind of problems as were in the law book. They're just all mixed together in one unit. Okay, 63. 63. Cosine 2x minus cosine x equals 0. All right. If they were both 2x, then I would just put theta in for the 2x like I showed you the other day. But they're not. One of them is a 2x and one of them is plain x. As soon as you see that, you look for an identity to change this one into plain x's, not 2x's. All right? And you look on your identity sheet. Now, the problem you're going to run into when you look on your identity sheet for cosine 2x is there's 3 options. For sine 2x, there's only 1 option. But for cosine 2x, there's 3 options. Here's the options. And I'll probably put it in thetas when I put it on your card, which
Sine squared.
sine squared, yeah. I'm having to think in my brain, yes, well, yeah, that's right, okay. I really don't know the other two. I have to rewrite this one by changing the cosine into 1 minus sine, and now I'm about to change that one into those are your 3 choices. Which choice do you think you should pick to work number 63? First choice, second choice, or third choice? Which one? Why? Yeah, pick the one that makes it all the same. If you're ever working a problem that has the sines only, use this one. If you ever work one that only has cosines, use this one. If they're mixed together, you probably need to use that one. All right? So I get 2 cosine squared x minus cosine x minus 1. Did y'all notice I changed the order of it as I was writing it? And then I hope that'll do what? I hope it will what? Factor. Somebody says, Mr. Evans, you're not supposed to combine steps on the little children. Fair enough. Honors class. All right, I put the trig identity in there and then I rewrote it. Why did I rewrite it in that order? Because it's going to do what? It's going to factor 2 cosine x, cosine x, a 1 and a 1, minus here, plus there. So I'm going to get cosine x equals -1/2, and cosine x equals 1. Cosine x equals 1 at 0, and 2 pi if you want to put it in there for her. Where does cosine x equal -1/2? Hey, what's going on? You can borrow whoever you want. Pi over 3, and then where else for -1/2? 4/3 pi. And there's all three answers right there. Notice you didn't have to wake him up. That's the good news. Your boy is probably down working with Roller. He better make an A on my test Monday. There you go. Is that all right? And that's a good problem, because it tells you what to do when you have a 2x and a plane x. And he's thrown several of those on there. Matter of fact, the problem I was working in the engineering class today, we used that rule because we had to rewrite something. Now, did I work the problems where you had to square both sides from the Miss Lyle's book, where you had to square both sides? Probably didn't, because I don't like it. This is something you very, very seldom ever do. Gosh, you don't want to start. I don't even like teaching it because you don't do it often enough that you should even probably know about it. But I'm going to talk to you about 61 and 62 here. And I think number 13 and number 20 need to be worked this way too, but we'll see. I think 13, 20, 61, 62 have to be worked this way. But let's look at 62. And I'm going to try to help you out on something here. All right. Here we go. 62. And I guess what bothers me about this is I never remember doing this when I was doing trig identities. I'm going to show you 62. It's got tangent x plus square root of 3 equals secant x. Now, what I would do, and what I always try to do, if I'm looking at a tangent and secant and I can't figure out what to do, I change them to sines and cosines. All right? If all else fails, I just change the sines and cosines. So what I did, somebody got sine x over cosine x plus square root of 3 equals 1 over what? Cosine x. And then I didn't like the idea of having cosine x is in the denominator. So what did I do? I multiplied everything by what? Cosine x. Or you can make cosine x the common denominator for everything. But I would just multiply everything by what? Cosine x. Get rid of the fractions. So I'm going to get sine x plus square root of 3 cosine x equals 1. And then my problem is I can't use the mother identity because that's not squared. See how I want to try to use the mother identity? I can't because it's not squared. All right? And somebody said, how about using the mother identity with the 1? I have never been successful by turning the 1 back into the mother identity. That is not something I want to do. I like just leaving the 1 there. But if you will notice, I'm having a real hard time coming up with a way to make this just sine x or just cosine x. All right? And I can't get it to where it's sine. I can't factor it. Can't get anything to work. You get to this point, you've tried everything. You square both sides. Okay? But don't start doing this on every problem because this is rare. but you square both sides. You can't figure out any way to isolate the sign. And if you'll notice, all your identities require them to be what? Squared, don't they? Right? Most of your identities. You square both sides. Well, when you square the 1, it's just 1. When you square this, you're going to get sine squared x plus 2 square roots of 3 sine x cosine x plus 3 cosine squared x. And then you realize that you have really messed up, Mr. Evans, because you can't add that and that together and get something pretty. So, you look at Mr. Evans, you go, Mr. Evans, you're not too smart. Yeah, I'll tell you why. Once you realize that none of that works, the best thing you can do is go back up here and square the very original. Oh, I knew that was going to happen. No, I didn't. I didn't know it was going to happen because you can do it with the sine and cosines. But in this case, since I couldn't make that look very pretty, I'm just going to square the very original. Square this side, square this side. Please do not do this until you have tried every other thing, looked at identities, because this is rare that you do this. Tangent squared x plus 2 times the square root of 3, tangent x plus 3, because square root of 3 times square root of 3 is 3. What method did I use that we don't talk about with the F word? I used the F word, right? Everybody knows I used the F word. Equals secant squared. Now, here's the moment that is absolutely wonderful. Yes, ma'am?
With the, for the square root of 3, for squaring it not into it.
Square root of 3 times the square root of 3 is 3. Right? Write it out twice and multiply it out. Right. Okay, do tangent x plus square root of 3 times tangent x plus square root of 3 and use it. All right? Yeah, I just did that in just one step. But here's the wonderful moment. Notice how you got tangents over here? See how you got these two tangents over here? There's an identity that will turn secant squared into tangent squared. That's what you want. Tangent squared x plus 2 square root of 3 tangent x plus 3 equals tangent squared x plus 1. That's the deal. See, you couldn't, when you had just plain tangent and plain secant, you couldn't ever convert the secant into tangents. But once you got it squared, you can change it. Happy? Get the idea? Please realize this is not something you do a whole lot. All right? Now, once you do that, you subtract the tangent squareds out, and you get 2 square root of 3 tangent x equals negative 2, because I'm going to subtract it. Then I'm going to get tangent x is equal to negative 1 over the square root of 3. Divide both sides by 2 square root of 3, and I get that. And get, yes ma'am?
Wouldn't it be negative 3? Instead of negative 3?
But you got a 1 over there. Wait, no.
Oh, okay.
No problem. I would double check me too in the afternoon. All right? It's not like I got to go and have a coffee break or eat a real lunch with an hour break. Take a nap in my office in the afternoon. And then you just look on your circle, and there is one problem. And we'll talk about that in a second. Where does tangent x equal negative 1 over the square root of 3? Come on, talk to me.
11, 6,
11,
5.
6 pi? And where else?
5, 6.
5, 6. 11, 6 pi, and 5, 6 pi. All right. I hate to tell you this, but you got to check your answers and make sure they work. Remember when you were working equations and you squared both sides to get rid of the square root? Remember that? Remember how you had those things called extraneous solutions? Yeah. You have to check for extraneous solutions when you square both sides. Check for extraneous solutions. And I'm going to show you why you have to do it. But anyway, you put 5, 6 pi in there in the original. And the tangent of 5, 6 pi is negative 1 over the square root of 3. Gosh, I don't even want to test it. Let me write it right here. I'm going to have to write it down to test it without the squares. I can't do it. Okay. So the tangent of 5, 6 pi is negative 1 over the square root of 3 plus square root of 3 equals, and what's the secant at 5, 6 pi? It's the reciprocal of the cosine, and that's what? Square root of 3 over 2? And, check it out, it does work. Think. Get a common denominator. Man, heavens, your brain is not working. Negative 1 over the square root of 3 plus square root of 3 equals square root of 3 over 2. Mr. Evans, that's a secant, so that should be 2 over square root of 3, and it does work. Okay, so that one works. Fair enough. Then check 11, 6 pi, and the tangent of 11, 6 pi is a negative 1. Secant of 11, 6 pi is still that, it still works. All right, so they both work. But always check them when you square both sides. And you just have to substitute back in and work it out and see if it really works. Does anybody know why you have to do that when you square both sides? Anyone want to know why? All right, yeah, I got some people who are awake still. All right, here's why you have to check for extraneous solutions when you square both sides. Does negative 5 equal 5? It doesn't, does it? But what happens when you square both sides? They end up being equal, see? So what's happening here is you might have a case where this comes out to be negative 1 and this comes out to be positive 1. Well, they're really not equal, are they? But after you squared them, they were equal. So that's the reason you always have to check for extraneous solutions after you square both sides. Now, I know 61 requires you to do that. Well, I'm pretty certain 61 does. And then everything else is pretty straightforward. 65, change that cosecant squared x into cotangents. Make everything cotangents and it'll work. Now, how many of you are finished with 6-2? 6-2 done, okay? If you're not done with 6-2 pretty soon, you're going to be in trouble, folks. You're going to do a little work on Friday. You may have to do a little work over the weekend. Does anyone have a question from 6.3 problem in 6.3 you're having trouble with that you'd like for me to work? Looking good? Okay. Okay, well, all right. We're ready for you to go to work. You start working problems and I'll try